To begin our study of geometric symmetry, we must first rely on the physical act of precise mathematical construction. This regular hexagon possesses an outer boundary called a circumscribed circle, which intersects every vertex. It also contains an inner inscribed circle that sits flush against the exact midpoints of all 6 sides. These two paths are concentric, meaning they share the same center point. This shared center is not a coincidence of drafting. It is a direct result of the geometric constraints we are about to prove. First, we define the requirements for a polygon to be regular. It must be equilateral, meaning every side is of equal length. It must also be equiangular. Every internal angle must carry the exact same measurement. Next, we define a geometric locus. A locus is a path or a set of points that satisfies a specific condition, such as maintaining an equal distance from a boundary. When 2 or more distinct locus paths intersect, that meeting point is the point of concurrence. We will now examine how these locus rules dictate that the centers of both circles must converge on a single point. This square, ABCD, serves as our test case for finding an inscribed center. For a circle to be inscribed, the center must be exactly the same distance from all 4 sides. We use the angle bisector as our locus tool. Any point along a bisector remains equidistant from the 2 sides that form the angle. The point of concurrence where these bisectors cross is marked as point O, our theoretical center. To define the radius of the inscribed circle, we measure the perpendicular distance from point O to any side, which we label OM. Using OM as our radius successfully inscribes the circle, making it tangent to all 4 edges. The symmetry of the square ensures that these loci converge to produce a valid incenter. To see why regularity is required, we can observe what happens when we isolate side length from angle measure. A rectangle is equiangular, with 4 90-degree corners, but it fails the equilateral test. As seen here, the rectangle supports a circumscribed circle, touching all vertices, but its unequal side lengths create a problem for the interior. An inscribed circle cannot exist because no single point is equidistant from both the long and short sides simultaneously. Conversely, a rhombus is equilateral, but fails the equiangular test due to its alternating sharp and wide corners. This rhombus supports an inscribed circle, but its varying angles prevent a clean outer boundary. A circumscribed circle fails because the vertices are not at an equal distance from the center. Without both equilateral and equiangular traits, the loci will not meet at a common center for both circles. This logic applies beyond the square to any regular polygon, from triangles to octagons. We can track this consistency in geometric property tables like Table 7.2, which document how the mathematical relationship between vertices and edges remains constant as side counts increase. As long as the geometric shape remains both equilateral and equiangular, finding a perfectly unified center becomes an absolute mathematical certainty. Whether you use perpendicular bisectors to find the outer circle or angle bisectors to find the inner circle, both paths intersect at the same point. This predictable scaling allows us to formulate a general theorem. These findings are synthesized as Theorem 7.3.1. First, the inscribed and circumscribed circles share an identical center. Second, this center is located at the concurrence of the angle or perpendicular bisectors. Third, the inscribed radius is perpendicular to a side, while the circumscribed radius joins the center to a vertex. Theorem 7.3.1 concludes that a circle can be circumscribed about or inscribed in any regular polygon.
The perfect symmetry of a regular polygon ensures these loci will always converge, beautifully unifying its internal and external boundaries into a single system.